Okay, so hello, welcome everyone to another lecture of thermal physics. And this week's topic, it's actually quite lengthy, and it's Boltzmann's entropy. Now, we are at the end of the module, and really the next bit for the next week is actually very, very light. The two remaining self-study packs are just for your own information, because there's no assessment at all linked to them, on Gibbs entropy, which is the generalization of Boltzmann's entropy for interacting systems, and the bit on the application of quantum statistical mechanics for identical indistinguishable particles to two examples of interest. That's a black body radiation problem and the free electron model, which are things actually that you have discussed already in condensed matter physics. So anyway, I mean, this is completely optional for you to look through, but I would encourage you to do it, because then you can put all the bricks together. So just focusing on this week's topic, that you can and you may want to extend over the next week, because it's quite intense, and that's fine. And there's again no assessment related to this, although this chapter is very important because it is actually examinable. So it's actually very examinable. So keep it in mind. Now, okay, so what are we going to look at in this chapter? But to begin with, we are going to think of the same type of system we were thinking about in the kinetic theory of gases bit. So it's a system of non-interacting particles. We think of a gas, an ideal gas with point-like particles, like I say, no potentials of interactions of any kind. And we are going to say how we describe the mechanical state and the dynamics of such system in a high-dimensional space. That's the phase space gamma. And then we are going to discretize this space, and we are actually going to change representation for what's known the single particle phase space, which we are going to see what it is in a moment. And this discretization will allow us to count the microscopic states of the system, okay, to enumerate how many of them there are. And then we're going to introduce the definition of Boltzmann's entropy. It's really a definition without further justification at first, but then retrospectively we are going to see the consequences of this definition, and we are going to see that this Boltzmann entropy, this just a mathematical definition, actually has the properties that we would expect for the true thermodynamic entropy of a system of non-interacting particles. Okay, so this is what we're going to see step by step. So we are going to define what a macro state of this statistical mechanical system looks like, and we are going to calculate the statistical entropy for an arbitrary macro state. It doesn't have to be a macro state of thermal equilibrium in general. And then we are going to specifically go to the equilibrium limit, so to the case of thermal equilibrium, and we are going to see what the Boltzmann entropy expression explicitly looks like in equilibrium. Now, that object should be somehow comparable, or should have the same kind of nice properties that we expect from thermodynamic entropy. And it does, okay? We will see it's additive. We will see that it's maximized in equilibrium when the system is thermally isolated, as per the principle of maximum entropy. And we are going to see that the temperature actually emerges naturally. So there is a parameter that we are going to call beta. It's in principle just a mathematical artifact that just happens to be the temperature. Okay, or more precisely, the inverse temperature. And from Boltzmann's entropy in equilibrium, we will be able to even derive or rederive the ideal gas equation of state. Without assuming anything, we just obtain the ideal gas equation of state. And to conclude, we are going to see a particularly important object, which is this partition function. We are going to say what it is. It's something that, if you know all the different states that your system can exist in, or the particles that make up your system can exist in, you calculate this function, and then from the function, taking logarithmic derivatives, logarithms, and manipulating that expression, you can get out directly, without doing anything else, the internal energy of your system, the entropy of your system, the free energy or Helmholtz free energy of your system, and also the pressure, okay, if relevant. So you can get all of that from the partition function. We're going to see how. And there are a few extra bits that are in this Boltzmann's entropy chapter in the lecture notes that I invite you to read, but I didn't go through in the videos because it would make it really long. So I didn't want to do that. There is a little discussion on Boltzmann's factor. There is a re-derivation of the Maxwell-Boltzmann velocity distribution, which anyway we already derived. You can do it from this classical statistical mechanics exclusively. And there's a final comment or remark in the very end about the technicality. So we will see that in calculating the equilibrium value of the Boltzmann statistical entropy, we are going to make an assumption. Okay, we are going to use a mathematical formula that's Stirling's formula to approximate factorials, large factorials. And this actually is only valid, well, if certain assumption about the phase space cells, these discrete units in which we are going to break down our the space of states of our system, if these cells are sufficiently large, okay, and we're going to make it's crucial to discuss how large they actually are. Okay, so in the end we are going to see that they are actually not as large as we would like to justify these formulas that we use, but we are going to see what way around we can justify that the results we obtain are valid or should be valid. Okay, so what needs to happen for our results to still remain valid? And it's a very mild requirement that is very easily satisfied. So we should be safe. Okay, so this is the outline, and we are just going to start with the lecture.